Hey, this is Nate here, and in this video I'm going to show some of the newest update to the Eclipse Light Engine and the features it has. The big one here is we now have directional lighting, and the ambient lighting model has now been updated and looks way nicer. It's a small update, but I'd say it's really impactful just because of that. Then also you see these numbers following the cursor. You can now get the light value at a pixel, which is really cool. And I want to say right away that if you are going to use that, it is an optional toggle on how to use it because it is very impactful to performance, and I'll go over how that works. And then at the end, I'm also going to explain how the ambient lighting normal is calculated. If you're not interested, don't. It's just there, kind of like a mini tutorial, because it teaches a little bit how the 3D math works to find the normal direction for that and how to set it. So just a bonus. So as you can see, this shadow, let me turn the ambient off first. You can see this shadow rotating around. This is from the new directional light. Before you had to make a giant point light, place it really far away, and turn up the attenuation and stuff, and that's how you kind of faked it. Now it's a real, actual directional light. It doesn't use an extra shader or anything like that. It just flips one of the bits for one of the values in the uniforms. So it's pretty much no cost directional light. It basically normalizes when it casts shadows. It takes the light, places it like right here, relative to the vertex of whatever shadow vertex it's doing. So they'd be the four corners of this box, and then it has a shadow length parameter now. So these shadows you can change, and by that length it'll offset it some, and that way every shadow casts exactly the same, and it's really cheap to calculate too. And then for the light itself from the directional light, it does the same thing, but it moves each pixel temporarily. It like moves it right under the light and calculates it. So real cool way to do it. And then the ambient lighting is you can now, of course, it has a intensity all the way to 0, all the way to 1, and it's purposely probably brighter than you would ever want it, but that's on purpose. The cap's pretty high on how it works. And if I turn it up just a little, you can now, let me zoom in, you can see I can rotate, change the elevation. So if I put the elevation way up like that, it's like it's right above the pixel, looking straight down, which, yeah, you probably don't want it that high, but you can also move the elevation up all the way down, kind of rotate it around. Looks good. Before, there was ambient lighting, but it was just really adding color value to a pixel, and it wasn't really true, calculated correctly. It was just a temporary sort of ambient light value. So now scenes aren't going to be as dark by default, and you don't have to add as many lights to make the scene look good and less, dreary and dark. Not everybody's making like a game with dark shadows and stuff. So, and then the color too. Right now the color's set pretty light. It's like a light green, so it's not as noticeable. But if you set a really strong ambient color, you'd actually see a huge difference on like changing the scene. So if this whole scene was like lava and volcano type looking thing, and you use like a red ambient light, you'd notice it quite a bit. So, and then the other thing I mentioned too, you can see I can get these light values, and I'll show you. There's two functions for that, and how they work. So here in the project, we have the new light object for directional lighting, and it's parented directly under the root light object instead of the light call object. You can see its children have all the other light types, and that's because directional light, you're not going to want to call it and remove it and turn it on and off the same you would the other lights, because it's global. It casts global shadows. It casts global lightings basically. And the new parameter is it has shadow length now. If we go back to the scene, you can see the shadow length that's at 100 right now, and if you turn it up and down, it'd be small, it'd be big. And also the way you set the direction, it has functions for set angle, set rotate angle, of course. But if we look at the room, I only have one placed. When you place it, it's just simply whatever rotation it has here, that's the way it's going to point. So the one in the example there, of course, it's rotating, but however you face it, the image angle is what it's going to use for its direction. So that's the directional light. And then the light engine, the new parameter for ambient lighting is ambient elevation. So before I had direction and intensity and color. Those are still there, but now There's elevation, and on the second part where I said I'm going to go over the math, I'm going to explain like what elevation really means. But the simple way to think about it, 90 is if you're going from flat with the ground and pointing straight up, that's 90 degrees. So that would be the lights directly above the pixels. So you can change the elevation. 45's default, and that's how ambient lighting works. Then the values here, we can get the light value. There's two new functions: lighting get pixel value, and then lighting get pixel value buffered. The first one here uses surface get pixel, which is, you can look at the GameMaker manual. It says it's very costly, which it is. Both of these are very, very costly. So use them only if you really need them. The big difference between the two is if you're going to get multiple light values in a given step, like many of them, you absolutely want to use the buffered version and not this version. This is if you only need to get one. And the reason is these do the same thing. They're going from video memory to system memory. They're copying a portion of it to a buffer, and they're reading from that buffer. And that cost is extremely high. It's about 3 milliseconds, at least on my PC, which this PC is pretty high end. It has a RTX, it has a really new CPU. Other PCs might not do so well. It will be more than 3 milliseconds. That's huge as far as budget goes, because you have 16 milliseconds if you're doing 60 frames per second, and you're using it all just to grab the value of a pixel. If you were to turn it off, the light, this whole scene right here, minus getting these two values, is probably less than a millisecond. I think when I've debugged it, or when I've ran the profiler, it's less than a millisecond to render. It's really, really fast. So you're using a way more budget just to get these two values. And that's because copying that memory from VRAM to system RAM is just expensive and slow. That's just how it works. Then, so this one here that I mentioned with the buffered version, that one you have to toggle enabled lighting buffer, and by default that'll be off in the asset. So you need to turn that on, otherwise it'll still work, it'll just return 0 every time. So you don't have to worry about it not being on if you accidentally use it, but you'll just get 0. So you have to turn that on, and turning that on, only do that if you're going to use it, because that's going to copy the light surface to a buffer every frame, with the intent that you're going to utilize that multiple times to get multiple values. So if your game needs it, that's the option. And the reason these two are both just as costly is because Surface Get Pixel essentially does the same thing that I just described, where it goes from VRAM to a buffer. I believe it just does a tiny portion of that surface, but that doesn't really matter because memory is contiguous when we're dealing with these buffers, VRAM versus system. So the copy itself is actually really fast. It's setting it up, allocating things, and then moving it. That takes basically a set amount of time. And so if I were to copy, like this screen here is 1080p, but if I were to do just a tiny like 2x2 surface, it takes about as long. It's not like, you would think it'd be much faster because you're only copying like 4 pixels, but it's not. It's actually almost just as slow. So Surface Gets Pixel, my assumption is internally GameMaker copies just a tiny little bit, grabs that value and gives it to you. This copies the whole screen and allows you to grab multiple values, because once you have it in the buffer, it's super fast. That's not a problem. The buffer, it just uses buffer peak and some math, and it grabs it from the buffer. So once it's done, it's cool. So you have a constant cost of about 3 milliseconds depending on your system. So anyway, that's it for the update. I want to go over, like I said, just the math on how the ambient lighting works and how the direction and elevation play into that. So if you're interested, this will be kind of like a mini tutorial on how that's set up. So here I'm going to draw out kind of how the ambient lighting normal is calculated. And if you picture a hemisphere, let's see, hope my art skills are good today. Hemisphere being, half of a sphere like this, and it'll make it look a little 3D. And it's got an origin, it's kind of in the middle. Let's use a different color. Like this is straight up, and then this is pointing to 0. and this so this is the elevation. This is where we're pointing straight up. So up here is 90, ground is 0. This is if we're looking at the side like this. So right here, this is for elevation. So we got 90 and 0. And then this 0 also, we have the direction of the light, which gives us the x and y, sine and cosine, and it goes around this circle all the way around 360. So if we make a top-down view of the same thing, and this will help to just draw these out. 0, we'll just do our unit circle by couple values. So, and if we were doing radians, we would have, you know, pi over 2, pi, 3 pi over 2, stuff like that. So this is a top view, side view, and the goal here is we want an x, a y, and a z. So, and this is kind of to teach problem solving and how to break down something like this to where we don't want to have to worry about the actual formula, because there's formulas and simple stuff that would do this for you right away. But instead, we're going to kind of derive to that by breaking things down and just parameterizing each value. And let's see what color. I'll use blue. No, I'll use this one. Actually, yeah, blue. So imagine the actual vector, direction, whatever you want to call it, for the ambient lighting is pointing kind of this way. And its direction is, if we top down, is 45, and here from the side is 45 elevation. That's not a 5. So it's 45 and 45. Should have gotten a thinner one. Okay, so, and it is pointing like that. So to parameterize it, we can look from the side. We can find this 45, the z value, really easy, because the z value is just right here. This distance, actually, use green. So this is the z value. This distance right here is z, and z right here is just sine of 45. That's it. So whatever elevation is, also right over here we have E. Elevation is some angle, so in this case it's 45. And just while we're at it, we'll put D. Let's put D for direction is 45. Just kind of a note. So Z equals just simply sine of 45. Or actually, again, my bad. We're parameterizing it. So sine of E. That's it. This distance right here, that's Z. That's how far it is pointing up. And then, while we're looking at this spot here, so that's cosine. But if we look at this distance right here, we'll just call that we'll call that just L for length. We want the length here, and it's going to be cosine of E. So it's that's this distance here, and we're going to use that. If we're looking here, and let's go to the top. We're at the top-down view, 45. So ignoring how long this is here, this line, let's just think about what is this as far as the direction goes if this were just 2D, and which would be sine and cosine. So we can start out x and y. So y is going to be sine of this 45 is the direction, so sine of d. And then the x value, so I should have drawn that out. The y value is here, x value is here, is going to be cosine of d. However, that's only if the elevation, if we were all the way out to here. But, right there, as the elevation changes, this point's going to move in more. So if we imagine we're looking top down on a hemisphere, and as the elevation changes over here, it's going to get closer and closer and closer. But that distance is what I talked about here, this L, cosine of E. So up here, cosine of D multiplied by L. And that's going to give us the XY for how far out here this is. So let's just say let's just say we were pointing this way, and our z was whatever. We want to know how far here, any of those directions, and that's going to give us a normal vector. So if we were to find the distance of all these, the total would always be 1, no matter what, which is great, because that's what a normal vector is, a distance of 1. So that's how we parameterize it, and we can go into Desmos. If you don't use Desmos and you are programming games, you need to use I use it all the time. It's very useful when you want to visualize how you're doing these things. So so the first two things, we had E for elevation and D for distance. So I'll just, you can't put, you can, if you put just E, you see how it comes out 2.71, that's a math constant. But if we put a 1, we can call it, so elevation equals 0, and its range is 90. And also, let's check, we are in degrees, so I'm doing degrees to keep it simple. So D, we'll call it direction equals 0. Oops. And it can go all the way in a circle, so 360. And let's look back. L is that length we had here, so L equals cosine of E. So we'll add that to expression, and we can just call L equals cosine of E1. Cool. I'll move these down. So as far as configuring the light itself, we're only going to be dealing with elevation and distance. And if we go back to Eclipse, you can see we have elevation and direction. Sorry, did I say distance? Direction. And if you ever look at like an actual diagram of this thing, the directions in a hemisphere, they don't call it direction, they call it azimuth. But GameMaker, people use direction more. It's more common and whatnot. So we have those two parameters, and now we want our x, y, and z, and they all equal something that we've now already made. So L is cosine. So wait, let me go back. Sorry. So we have our x, and if you don't put the 1 there, it's gonna do the actual like the graphed point automatically. We don't want that, so we do put the 1. So remember, x is cosine of the distance, d1, times L. And then y equals sine of the same thing times L. And then z was just really simple. It was the sine of the elevation. Check back. Z sine of E, so sine of elevation. So if we change these, you can see the numbers change. Oh, E1, there you go. But by looking at this, you might think, well, is it working? What's it doing? So we can prove that it's working. We call it? We'll just call it N equals. So we'll do the distance formula. The distance formula for 3D is the same as 2D. You just add another component. So if you ever get into 3D math, you're going to often hear it's the same as 2D, just add a z. And it does happen that way quite a bit. So x1 squared plus y1, y1 squared plus z1 squared. And as you can see, n equals 1, and no matter what I change these to, it's always 1. Because this is the beauty of sine and cosine, and why they can do so many awesome things is it allows us to parameterize things and stuff. And so what you can see is, instead of having to think of a formula on how to find like memorize or know something, instead I just broke it down into these different parts. I looked at a side view and a top view, and a lot of the times that's what you do with 3D when you're dealing with a z value in 3D. You look at the side view, and this side view is really easy. It's just 0 to 90. Sine and cosine is going to give me these two distances within that 0 to 90 arc. That's it. So we define this L value here, this length, which is cosine of E. Whoa, what did it do? And then Z is just the sine, how far up that is, which alters how far this top view, the X and Y, is pushed out from the center. So, and that's it. That's how it finds the normal, the X, Y, and Z. And then over in Eclipse, Where did I put it? On the create, the light engine itself. Let's make it bigger. Probably put it down here. Set shadow. There's a lot. Update ambient parameters. So I call it ambient X, Y, and Z, and you can see these are those same. I spelled out the variables, of course, but ambient direction times those, and that L value is, and I'm using decos for its degrees. Normally, radians are better when you're working with game math, but you're not going to change this nonstop. It's not a huge deal. But so, and then we got to flip the sign just for surface reasons. But other than that, that's how it works. Hopefully you learned something too at the end of this video instead of just the other parts. So anyway, thanks for watching. Like, subscribe, stuff like that to hopefully get more eyes on stuff like this. So thanks for watching.